for organizing this, Nancy, and all the Texas A&M folks. I have about, I think, a dozen new research ideas just listening to other talks today. I think it's terrific to have such a great interdisciplinary group of speakers in the robotics field. In robotics lately, I guess most of the things that myself and my students talk about at robotics conferences are things related to medical robotics. I kind of wanted to go back in this talk and talk more generally, though, about haptics and the field of the sense of touch. This has already been mentioned in several other talks related to simulations and medical robotics applications, but I'd really like to get people thinking creatively about what we can do with the sense of touch and what some of the interesting engineering challenges are. So I want to start with thinking about the different senses that we have, sight, hearing, smell, taste, and touch. And here's some of the folks in my lab demonstrating the senses or lack of these senses. And we're very familiar with all of these as being an important part of our lives. But robots, compared to us, as well as virtual environments and teleoperation systems, they're deprived in having a lot of these sensory capabilities. And that's part of the reason that we have such challenges in working with these systems. So as we think about how to design and what senses to pick out for the systems that we're developing, you can ask a couple questions. So one is, as a human, which sense is most valuable to you? And that's kind of a difficult question to ask. So here's another way to ask it, to say if one by one, each of your senses were taken away, which is the last one you would give up? So I'm going to take a quick poll. Who votes for sight or vision? Usually that's our number one winner on vote. Hearing? Maybe a couple? Smell? No votes. I think on one group, it was actually, I got one. I once talked to a group of Korean automotive engineers, and they all said smell, and so there may be a cultural thing involved there, I'm not sure. Taste? Not so much. You enjoyed your Texas barbecue without taking that. And then last is touch. Thank you very much. You all know I'm a haptics researcher now, and I appreciate your throwing me a bone. Well, there's no right answer or wrong answer here, of course, but mine would be touch. And part of that is some evidence of what happens to people who actually have specialized diseases which make them lose their sense of touch. And in fact, if people are interested in this, there's a great BBC documentary called The Man Who Lost His Body about a person who had large fiber sensory neuropathy and lost his sense of touch basically from the neck down. And it might be even more profound than we realize, because he didn't just lose his ability to know if something is soft or hard, he also lost his ability to know where his body position was in space. And this is the sense of proprioception and the knowledge of where your limbs are in space. And so, just a little lunchtime activity, you guys will experience the need for this sort of proprioception by doing a little task. Everybody raise 2 hands in the air, point your fingers up, don't look at them, put your fingers together, and try to touch the tips together. All right, you were cheating, I thought. So the way that you do this task without looking at your hand is that you use your sense of self, this proprioception. So how is it that you even know where your limbs are in space? Well, it's a combination of feeling muscle forces, and you're pushing against gravity. And then there are other parts of that sensation that you may not even realize that you're getting. So it turns out that skin stretch, the actual stretch of your skin over a joint as you rotate, say, a wrist or an ACT joint, actually gives you a lot of cues as to where your body is in space. And without that ability, you get people who, in order for them to even just move around and do the activities of daily living, it's incredibly difficult. They have to constantly visual servo to figure out what they're doing. So obviously the robots that we typically design have a sense of proprioception. We give them kinematic equations and joint sensors. But it's that combination of proprioception along with exteroperception, that is feeling things in the outside world, that all has to be integrated in terms of us interpreting both the world around us and what we're doing within it. Now, if we want to think about what happens when you lose certain senses of touch, and in this case, I'm going to split this into 2 main categories. One is cutaneous sense, which is sensing in the skin, gives you information like texture and local stiffness. And then there's kinesthetic sense, which is proprioception, knowing where your body is in space, and also large-scale forces like feeling the push that I'm putting on this table. You might have experienced losses of those senses. For example, if your skin gets very cold, your little mechanoreceptors go dead, and you have trouble buttoning up your jacket when you're skiing, for example, not because your muscles are getting cold, even though it may feel like that's what happened, because you don't know the local contact conditions between your fingers and the environment. So obviously this is something that robots need, and very, very few robots have. Proprioception, which is part of kinesthesia and force sensing, you lose that if your foot goes to sleep or your arm goes to sleep. And before you get that horrible, painful tingling sensation when it's coming back to life, you also feel this loss of kinesthetic sense. Or if you've ever had an epidural, like I have, then that is also an experience where you feel like your body is kind of dead to you. And so maybe it gives us some cues about what it would be like to be a robot without the inherent senses that we have. There are other types of specialized groups, patients in this case, who have lost their sense of touch in various ways. So a prosthetic arm, for example. If someone is to understand how to control a prosthesis, that sensed information not only about contact with the environment, but also the configuration of a complex, high degree of freedom limb has to be fed back to the human operator somehow. And in the haptics field, people have designed sort of body wearable tactile displays to try to communicate that information. But the really exciting stuff, I think, that's going on is how do you actually feed that information directly into the brain through some kind of implant. But our understanding of even how humans interpret this information is still at such a basic level that we're not able to really display the natural feeling of controlling an artificial arm. Now, the way I think about prosthetics like this limb is that it's actually a teleoperated robot. So if you think about it, a teleoperated robot is where a human sends commands, so the human is the master, sends commands to a remote robot, the robot does their bidding, and then the human hopefully will receive some sort of feedback. And it just happens to be that this is a teleoperated robot that is directly attached to the body. But there are lots of teleoperated robots that are operated all the time in space, for explosive ordnance disposal in the field, and my favorite, medical robotics, which are all scenarios where people, whether they're surgeons or people in the military or an astronaut, have to remotely operate a system, and they've lost their sense of touch. They have limited understanding of the proprioception of that remote robot, and the external feedback, that is feeling the environment, is also mostly lost to them. And then even more broadly, if you think about human-machine interfaces in general, I love this image from Tom Ego's book on human-computer and human-machine interfaces, which is our sensory interaction with devices is so incredibly impoverished. This image is supposed to represent how your computer, your smartphone sees you. You know, maybe a finger, 2 fingers, if you've got multi-touch, I guess. One eye, because you don't really have a 3D display, and maybe stereo audio, but that's it. This is how you look, you know, to the devices that we interact with every day, and it could be so much richer. So for people who are not familiar with the haptics field, just as a quick introduction, I'll explain to you how we usually think about this technology, how it works. So here I show a user. This user happens to be Ann Mayovich, who's over there, and wave her hand. She's a former PhD student of mine who is now here in Texas at UT Dallas, an assistant professor. And what she's demonstrating here is that she's moving around a typical commercial desktop haptic device. This is a kinesthetic device that's really designed to provide force feedback, and it's recording her movements at the red dot at the tip there. And then in a virtual environment, her movements are being tracked, and if they collide with objects in a virtual environment, which we get to program, then forces will be sent back to her to represent the forces of that interaction. And this loop has to run, the rule of thumb is about a kilohertz for it to feel really crisp and compelling and to also maintain system stability. It's not, of course, all about virtual environments. I'm also interested in teleoperation. So now you can take that virtual environment and you can replace it with a teleoperated robot. And that robot has sensors to know about how it's interacting with the real world so that those interaction forces can be fed back to the human operator. But the basic idea is still the same, and there's all sorts of interesting problems related to both the human perception, the stability of the control loop, as well as how do you actually design the sensors and actuators and mechanism to provide this sense of telepresence and this ability to interact with a remote environment. And when I say remote, sometimes we're not talking about remote in terms of miles and distance, but sometimes in terms of scale. So that's one reason why surgical robotics can be so useful, is because it allows you to scale down the human operator's hands and put a robot inside the patient. If the human is going to teleoperate that robot, you need to have this sense of transparency. Of course, not all haptic devices look like the one that I just showed. Here's an example of a body wearable system, and systems of this type have become popular in the last decade or so. Devices that you can wear on different parts of your body, which in this case, like Michelle is demonstrating, provides vibrotactile feedback. And so she's tracked with her movement by, in this case, a Connect system, and she moves her arm to a particular location. But let's say a rehabilitation or yoga training example, we want her to move her arm here. Vibrations can be sent as signals to get her to move to a different configuration. So back to another type of system that could use haptic feedback, looking at teleoperated surgical systems. This is the Da Vinci surgical system, which I should disclose provides some funding to my research lab. This teleoperated robot works as follows. The human operator sits at this master console and manipulates a fancy high degree of freedom, 7 degree of freedom pair of joysticks. So he can move an XYZ, yacht, pitch, roll, and gripper. And then he controls a remote robot where although the robot looks kind of big and scary, what actually goes with the patient are very small instruments. The whole idea trying to be more minimally invasive than a clinician could do with his or her hand alone. And from the inside, these systems would look like this. There is definitely a scaling here. This will show up in the split screen in just a second. And just note there's about a 10 times scaling in the positions of the user's hand and the instruments at the tip. But as was mentioned in some of the other medical robotics talks, most of these clinical systems don't yet have haptic feedback to the user. And in this case, I feel like the big challenge in our field is actually not so much how do you give the forces back to the human operator. I think for the most part that problem is really solved. We can actually push back on the user's hands. The question is twofold. One is, how do you actually sense the interactions with the patient? How do you actually estimate what the forces are? Or if you want to really know the detailed contact conditions, how do you know what that distributed contact information is? And on the other hand, if you're providing feedback to a human operator and you're pushing on their hands and they respond to that, that closes a loop which can cause very interesting control issues. You can have instability if your loop is too slow or if your stiffness is too high. And there's an inherent trade-off in teleoperation theory about having very high transparency, that is feeling the environment remotely exactly as it is, and stability. And you cannot have both perfectly. And so we're always trying to push the envelope with the way that we do the control to try to make that trade-off a little bit better for us. We've also demonstrated that it's really not just about pushing on the hand, which is the only useful thing. Sometimes just the information about haptics is useful as well. So here's an example with a clinical Da Vinci robot, where over here we just have dots that change color that give someone a cue about how hard they're pulling. And in this case, they can do a better job of not breaking a suture. They have that sort of visual feedback. But then there are other tasks where really pushing back on the hands is very necessary because of the way that people seem to process touch and spatial information. So in this case, someone is palpating. Now, not a manipulation task, but an exploration task to find a hard lump in soft tissue. Just like we mentioned, you'll have hard lumps that might represent cancerous tissue and has different properties from outside tissue. And it turns out this sort of graphical feedback, this visual display, isn't nearly as useful for people finding lumps as actually pushing back on their hands with real haptic feedback. So sometimes you can use these sorts of sensory substitution, but not always. Other things that we're trying to do to push the envelope on what kind of feedback people get is actually understand more about what sort of feedback is useful to people. So if you are pushing with a pen or a stylus on a surface like is shown in the image there, the information that you get is both cutaneous and kinesthetic. You get skin stretch on your skin as well as gross force feedback on your limb. And it turns out you can trick users to thinking that they're feeling forces even if you're just stretching their skin a little bit. So we build these little tactors, this little red button which can push on the skin and give users the feeling of forces without actually pushing on them. And here's an example of such a system you use in a virtual environment. Normally the fingertip would be over the red dot so they could feel the skin stretch. But let's see, move his hand out of the way so that you can actually see the red dot moving relative to the surface that it's on. And the idea here is that you can trick people into feeling forces, even if you're just stretching their skin. And you do that while breaking the closed loop kinesthetic control loop, which can lead to instability. And it turns out people can interpret these skin stretch cues very readily and very intuitively. Another very interesting area, and this was already discussed in the area of dental simulation, is that simulation is also really important as both for training people to use robots and also as an application of robotic technology. And so while there's clinical systems to do this, or that are already used clinically, like the one on the right shown here from immersion, what we're trying to do is push the envelope to more interesting types of displays where you actually can get a full hands-on experience. Well, there are many procedures where you operate through tools. Dental simulation and laparoscopic surgery are two examples of that. There are a lot of cases where you really want to learn how to palpate with your own hands. And so we've been looking at how do you create surface displays who can change both their mechanical properties and their shape simultaneously, so that you can form a sort of digital clay that can generate some arbitrary set of properties at any particular time. And this is just a first step towards this. This is a funny little device that my student designed, which uses the concept of particle jamming, where you have cells or membranes which are filled with a granular material, in this case coffee grounds. And when you vacuum the air out, those cells become very hard and stiff. And when you let the air in, they become soft, just like a vacuum-packed bag of coffee that you want to buy at the grocery store. And then there's also pneumatics coming from underneath to sort of blow the surface up and allow you to create different shapes. We're in the process now of building a 100-cell array, so not a kilobot, but a hectobot, I guess. And we're not quite ready for prime time yet, so I'm not going to show you pictures of the device, but we're able to do simulations to show what kind of shapes we can actually achieve with a device like this. And it's a little bit different from pin arrays that people sometimes think of in terms of haptic displays for surfaces, in that it's more continuous. And so that can give you more shape control in some ways. In other ways, it's also a filter that sort of damps out some of the sharp edges that you would like to display. So ultimately, this and other types of tactile surface displays present a huge opportunity and challenge for these devices. So I'm going to end by talking about haptics in a different context, which is education. This is something very important to me, very close to my heart. As many of us know in robotics is a huge inspiration for students to get involved in science, technology, engineering, and math topics. And haptics, I think, has the same capability, but maybe a little bit of a different focus. And so we have students that come into our lab all the time and feel these demonstrations, or we bring them elsewhere, which is kind of nice because we have very small desktop devices. And I love this video because these kids are just climbing all over each other to get their hands on these haptic devices. But what they're feeling here is physics. So they don't know, but we're teaching them physics. We're saying, this is a virtual spring, this is a virtual damper, here's the equations that we rendered, and now you can connect it to something that you intuitively feel. So last year, we got interested enough in this to say, could we actually use haptics as a way to reach students that might not otherwise have access to this kind of technology? And so we designed an online class where students had hands-on haptics labs. And I'm very passionate about laboratories and hands-on work, and I feel like that's something that's really missing from online learning in general. And so this was an experiment to see if we sent haptic devices that students remotely had to assemble, and this is the device that we designed for that, called HapKit. Could they actually do these labs in a remote way and take data and send it to us and have us be able to understand whether they had a good laboratory experience or not? And while this was very challenging and took up a lot of time, it was very rewarding to see that compared to most online courses, we had almost 80% completion rate, and people were very engaged in the whole process. And having a device and having a hands-on experience was super important to them. And so, by the way, if anybody, this is all open hardware, open source, so hapkit.stanford.edu if you're interested in a design. So haptics going all the way from helping an expert surgeon learn how to use a surgical robot, all the way to a high school student who we're trying to give them a tacit knowledge of physics by giving them a physical experience, are all examples of how haptics can influence how people learn and perform. And with that, I'll thank you and take some questions.